Hello, welcome to webinar number 13 on spherical lenses and mirrors. So today we'll be talking about this wonderful things called curved mirrors, and they are quite fascinating. I think lenses are studied in school, but mirrors are not so much. I think students tend to find them complicated. So hopefully today I'll introduce you to the mirrors, and hopefully we'll get some. Um, well, so hopefully you'll like them more after this. So what I'm going to do here is I'm going to just talk briefly about what does a mirror do. So a mirror can create an image, of course. And so what does that mean? Well, if you place an object in front of a mirror, like this. So this is an object. I don't know. I like to think of it like a Christmas tree, right? Right? So when I draw an arrow pointing up, I mean a Christmas tree. Sorry. Okay. Now, light from that object will hit the mirror, and there is the radius of the curvature. Apologies. So just yeah. So there's if this is the focal point, then a distance twice the focal point. That's the center of the circle. So the mirror is a sphere, and C is the center of that sphere. Center of sphere right. So that's the sphere, imaginary sphere. And there are interesting points. So that's a bit too far. So let's make the object somewhere here. So if you draw a line from the center of the sphere to the tip, this light will obviously reflect back exactly to the same direction, because light will reflect. So light coming from this end, going in this direction of the mirror, it will reflect directly back. Now, the second ray of light we draw to the center of the mirror, so like this, and it will reflect at the same angle but backwards. Okay. So light will come from the object and it will reflect that way. And where these two rays meet will be the position of the image. So if we take that line and we extend it, not this one, I meant this one, but it doesn't really matter. Okay, if I extend that line, and if I extend that line, that's where my image is going to be. Image. So it's an upside down image, so it is inverted. It is real, and it is magnified. Magnified. Similar to lenses, right? So, do you understand this diagram? Do you understand what I've been drawing here? On a scale of 0 to 10, please. Okay, great. That's nice. So let's look at this one, this question. A beam of parallel rays approaches a concave mirror at a small angle to the principal axis. So we have a parallel beam of light. So let's say we choose a color. Right. So parallel beam of light. And it says that it will show that the reflected rays intersect at the focal plane. So the focal plane is this imaginary plane. So this is the focal plane. It's an imaginary plane containing the focal point. And the rays should converge here. I don't know why I'm drawing them with green. Always say they should be the same color. They will meet at this point. So the rays should all reflect into this single point, and that point should be a distance. This distance should equal to focal point multiplied by the angle alpha, where alpha is this angle. So that's what we're trying to prove. Okay, so let's do this. So let's take this another copy of this, and we know r is the radius of curvature, r, and this point is C, and the focal distance is F. We just erase this. And okay, so what's going on? So let's send a ray at a small angle. Small angle alpha, and it will hit the center, exact center of the sphere. So it would reflect at the same angle, of course. It would reflect at the same angle, alpha. All right. And what we're trying to prove, that all parallel rays would meet the reflected of each ray. We will reflect here, and that distance is equal to alpha f. Well, for the first ray, it's very easy to prove, because if this angle is alpha, that means that this angle is alpha as well, and this distance is f. So tangent alpha is equal to d alpha f divided by f. So we use this triangle, but f cancels and it's equal to alpha, and this is true for small alpha. So that is true. So the first ray definitely goes through that point, goes through point P. So this is the thing we're trying to prove. P. So P is alpha f away from optical axis. Nice. Now let's take another ray, which is slightly offset. Slightly offset. And let's say it is offset by a distance, well, let's say x, right? Now, if we look closely, it will hit the mirror. So let's say it will hit the mirror, and let's say the mirror is obviously not vertical at this point. It's at an angle. And let's say that this angle is beta. So the mirror, maybe I can make it more pronounced, like this. And the mirror is like this. That's the tangent. And this is x. This is x. And if we have a tangent here, let's say that this angle is beta to the vertical. Beta. That means the ray reflecting from that, so the ray incoming is alpha, and the reflected ray would be alpha plus 2 beta. Alpha plus 2 beta. And this distance, this is x, right? And so we need to prove, we want to prove that tangent of alpha plus 2 beta is equal to x plus alpha f divided by f. That's what we're trying to prove. So for this triangle, right? And yeah, so we just need to find beta. If we take a sphere of radius r, and we step away and distance x from the middle, x, and this angle is going to be beta, and we can say that sine beta is equal to x divided by r, because this is r, this is x. So sine beta is x divided by r. But beta is small. So beta is x divided by r. But we also know r is 2f. But we know that the radius of a sphere is double the focal point. That has been shown in the assignment. And so beta is x divided by 2f. In other words, and we can sub that in. Right. These angles are small, so that's equal to alpha plus 2 beta equal to x, and x is 2f beta plus alpha f divided by f. F cancels out, so alpha plus 2 beta equals 2 beta plus alpha. True. So that means that the second ray, so let's label them. There's the first ray, and the second ray. True for small a. So ray 1 passes point P. And this means that the fact that this is true, that ray 2 passes point P. And thus we have proved that the two rays meet at a point P, which is alpha f away from the point. I hope that makes sense. I think it's one of the harder questions of today. But right. We could do it in a slightly different fashion. We could say, okay. Oh, no, that's not it. Ah, yes, that's a good point. Why is it alpha plus beta? That's a very good question. Thank you for asking that. Um, it is not very obvious. No, right. So imagine that this angle is beta, and we have a ray. I like that you're asking that question. That means you really understand stuff. Um, we have this angle is alpha, and you need to draw the normal as well. So the normal, this is the normal. So this angle is beta. And when you reflect it down, this angle is going to be the same as the angle of incidence, but the angle of incidence is alpha plus beta. So this is alpha plus beta as well. The angle of incidence is equal to the angle of reflection, right? Because the angle to the normal is equal to the angle to the normal. And therefore, if this angle is alpha, then this angle is alpha plus 2 beta. Does that make sense? Because the there's the normal line, which is an angle at beta and reflects. Yes. Um, so we could say that, all right, so we've got a spherical. We could try to do it in a slightly different way. Let me do this again. Right, I'm spending half an hour on one question, but hopefully I can do it quickly. Different way, different approach. Right, so the different approach goes the following way. So you already know, you already so you already know that ray one passes through that given point. So we don't care about that point. We want to know, where does the second ray, where does second ray meet the focal plane? That's the question we're trying to answer. And let it be at point X. And let this distance be Y. Right, so the ray travels here, hits the mirror at point X, and reflects into this. And we know that this angle is alpha, and this angle is alpha plus 2 beta. 2 beta. And this is, of course, X. So we can say that tangent of X plus Y, tangent of alpha plus 2 beta is equal to X plus Y divided by F, because this is F. Therefore, we need to find Y. So Y is equal to F multiplied by tan alpha plus 2 beta minus X right? Yes. But we note that alpha plus 2, tan alpha plus 2 beta is alpha plus 2 beta. So y equals f multiplied by alpha plus 2 beta minus x. And we've seen previously that if we, for a sphere, if this is x, then this point, and if this is beta, then sine beta equals beta, which is equal to x over r, which is x over 2f. So x is 2f beta. And so that's equal to f alpha plus 2 beta f minus 2f beta. 2f beta cancels out, and we have f alpha. So we've proved that any ray, that a ray approach a ray which is shifted and distance x will go through the focal point a distance f alpha away. So that means any ray will pass through that point. So conclusion. Any ray parallel to the first ray, to one, will cross the focal plane f alpha away. Right. Okay. Moving on. Objects inside the focal length. So this is yes, a concave mirror. Object is placed a distance smaller than the focal length. Draw the ray diagram using 3 principal rays. Okay, so literally that. Now we need the we need to double the radius of curvature. So let's do this, and that's the center. Okay, we're going to use that. That's C. That's okay. And now we draw a line from the focal point to here, and that comes out parallel. The focal point is given. It's half the radius. Focal point is the half the radius of the why is it not? Ah, that's very annoying. Okay. Half the radius of the curvature. Okay. So the first ray goes through the focal point, well, as if it is coming through the focal point, and comes out parallel to the original one. The second ray, you can always draw a copy of Q. So you copy Q and draw it like this. Okay, I'm just going to use a ruler. Ta-da! So that's 1.7. 1.7 centimeters. Right, so the second ray passes, goes from Q, and then through this one. Okay, and where the two rays meet, so this is ray number 1, this is principal ray number 2, and where the two rays meet, of course, they don't meet, their extensions meet. Okay, this is where your image is. So this, when they ask you to construct an image, that's how you do it. So this is Q, and this is the image. Now, the rays, if you trace the rays don't actually intersect here. So this is, and the image is behind the mirror, so there's no way it could be a real image. So rays don't actually cross at the image. You can see that the ray from Q, it goes like this and then reflects like this and then goes from here and goes here. So they don't meet. So this is a virtual image. If you place a screen at that point, you would not see anything on the screen. Virtual image, then it is enlarged and it is upright. So not inverted. Lovely. So it's virtual. Whether the image is upright, it is upright, and it is magnified. Okay. It says using 3 principal rays. Okay, the third principal rays goes from the center. The third principal ray. So let's draw the third principal ray as well. So you draw a line from the center of the sphere and back, because it reflects exactly backwards. So it goes here and then reflects directly backwards, and that's the third principal ray. And if you continue that line, it will meet at the same point as the image. Right, so 3 principal rays. So one goes through the tip and then from the focal point and then reflects parallel. This second one goes from the center and back, and the third one reflects from the vertical part of the mirror, so where the mirror meets the principal axis. Okay, determining a focal length from magnification. A concave mirror forms a real image with magnification 4. When the object is moved 3 centimeters closer to the mirror, magnification becomes 6. Determine the focal length of the mirror. Right. So here we can use the formula. We can use the formula for the we can use the formula. So the real image, real means positive. DI is the image is positive, and negative to a virtual. Lovely. So in the first instance, we have magnification 4. So DI over DO is 4. And then I is 4. When it's moved closer, that means that the object becomes 4 centimeters closer. So second, d di dash divided by do minus 3. So it becomes 3 centimeters closer, and that becomes 6. That's the new magnification. So we can write the di. Is that enough information? Di image. Okay, di is 4d0. And here di dash is 6do minus 18. Di dash is the new distance. Oh, we need the focal. We need the focal length. Okay. The 1 over d0 plus 1 over di is 1 over f. And we can see that di is 4do. So 1 over do plus 1 over 4do was 1 over f. So f is equal to 4 4do over 5. And here 1 over do minus 3 plus 1 over di dash. This is a new position equals 1 over f. Okay. And so here, oh, yes. Yes. do is 5f over 4. Brilliant. And here di is 6do. Di is 6 multiplied by 5f over 4 minus 18. So this is 2, 3, 15, 15f minus 36 over 2. And di dash. So we just need to plug this into here and plug this into here. So 1 over 5f over 4 minus 3 plus 1 over 15f minus 36 over 2 equals 1 over f. And then hopefully get an answer. So let's try to simplify this. So this is 12 and this is 4. So 4 5f minus 12 plus 2 over 15f minus 36 equals 1 over f. So we multiply everything by f, multiplied by 5f minus 12, multiplied by 15f minus 36, and we get 4f 15f minus 36, 2f 5f minus 12 equals 5f minus 12 multiplied by 15f minus 36, open brackets, 60f squared minus 108. Is it? No, it's not. 144. 144, is it? Yeah, 144f plus 10f squared minus 24f equals 75f squared minus 580f minus, okay, my mental maths is at capacity at the moment. 180 plus 12 times 36 times 36, 432. 432. Okay, so it's a quadratic equation, not too bad. So 70 minus 75, so 5 f squared. 180 f 180 f 75 minus 180 minus 180 f. Okay, minus 360 plus 144 plus 24 minus 192, so it's minus 192 f, and then 432 plus 432 equals 0. And now we just solve a quadratic equation. 5 minus 192, 432. And it's either 36. So f is 36, or f is a 12 over 5, so 2.4 centimeters. Though f is cannot be 2.4 because it says that, oh no, it could be 2.4. Could it be 36 though? It becomes closer. So it's a real image. That means it is further than the focal point. So the focal point can be 2.4. Can it be 36? Probably. Looks like it can. Let me check with the answer. The answer is 36. Why is it not 2.4? Let's see if that makes any sense. So you have a mirror. You know, the focal point is 2.4, let's say, and then another 2.4. That's the radius. Now, if you want a real image, it has to be further than the focal point. So the object has to be here. Oh, and it's enlarged, of course. Well, it's if it's enlarged, then it has to be between the radius and the focal point. Yes, it should be 36. So, answer. Okay, I'm not convinced. 36 centimeters, F. I'm not convinced that 2.4 is not a valid solution. Let's check if we can actually do the experiment. Spherical mirror. Okay, we need a radius of curvature 70. So if you're closer than the focal point, then the image is going to be virtual. So this has to be a real image, so it's further than the focal point. And magnification is bigger, but look, as you move away, yes, okay, that makes perfect sense. If you double the focal distance, so the focal distance in this case is 90 millimeters, so 9 centimeters. oh no, that's centimeters. So 90 centimeters is the focal distance. So if you move further away from the focal distance, you can't have magnification of 4. It doesn't make any sense because the diminish. So imagine this is 2.4 centimeters. In order to have magnification, you have to be between 1 and 2 focal points. But if you are, okay, that makes perfect sense. 2.4 is not a valid solution. 2.4. So imagine that this is 2.4, 2.4, and the double focal point is another 2.4. F equals 2.4 4 centimeters is not a valid solution. As to have magnification greater than 1 and real image, the object must be D object must be more than F and less than 2F distance. But if you are, so that means D0 is between 2.4 and 4.8. But if you are between 2.4 and 4.8, if you move 3 centimeters, you move out of that range. Moving by 3 centimeters takes you out of that range. Takes you out of that range. And that's the explanation. I hope that makes sense. Right, so the answer is 36. So not 2.4. Convex mirror and image position. An object is placed 15 centimeters in front of a convex mirror. So convex mirror, yes, like this. The focal distance is minus 10 centimeters. Right, so we have an object, 15 centimeters. So this is the focal distance, so that's 10 centimeters. And you're placed here. This is the object. So this is DO. DO. And we write the equation of the mirror. Now, 1 over DO plus 1 over DI. And let's look at the rules. Let's look at the rules. Positive D0 is always positive. Positive DI corresponds to real image, negative to virtual. So a convex mirror will give you a virtual image. Positive F corresponds to a concave mirror. Right, so DI, the distance. So that means D object is 15 centimeters. The focal point is negative 10 centimeters. And DI is going to be the image is going to be negative. Is negative. Negative because it's a virtual image. Virtual. And we can show that if we take a convex mirror and the focal point is 10 centimeters. So let's change the focal point to about 10, and we place the object at 15. 15. We can see that it's a virtual image. It's behind the mirror, so it cannot be real. This is the situation. And let's see if we can get a reasonable answer. Okay, virtual. So we have d1 over d0 minus 1 over d1 equals 1 over f. So 1 over 15 minus 1 over di equals 1 over f. So 1 over negative 10. And so 1 over di equals 1/15 plus 1/10. So that's 30. 2 plus 3. That's 5 over 30. It's 1 over 6. So di is 6 centimeters. So it's 6 centimeters behind the mirror. And let's see. It does look like it. So this is 15. So the 1, 2, 3, 4, 5, 6. Yes, that is 6 centimeters. You don't have to use the minus. Then you just get a negative answer. And negative answer means it's behind the mirror. So if you do this with the plus, then di is minus 1/15 minus that. It's minus, minus, minus. So di is minus 6. Minus means virtual. Yeah, I think that's better. Minus means virtual. Lovely. Moving on. Converging beam incident on a mirror. The converging beam approaches a concave mirror. The extensions of the incoming rays meet 30 centimeters in front of the mirror. After reflection, the rays converge at point 20 centimeters in front of the mirror. What does that even mean? Like, what are we talking about? So a converging beam and approaches a mirror. All right, so it doesn't specify whether it's parallel or not. So we're just going to assume, sorry, it's a converging beam. Right, converging beam. So like this, converging beam of light. The extensions of the incoming rays meet 30 centimeters in front of the mirror. All right, so they meet 30 centimeters in front of the mirror. After passing that point, they reflect and they meet again. They meet again somewhere here. Imagine they would meet somewhere here, 20 centimeters in front of the mirror. 20 centimeters in front of the mirror. Right, so I hope that looks all right. And it looks very messy, but until you start thinking about it. Why don't we replace a converging beam? A converging beam meets at a point. So why won't we just treat that point as a source of light? Think of this point as the source of light. Because if a beam is converging, that means all light rays pass through that point. So we could think of it, that point as the source of light. And therefore, the question becomes incredibly simple. You have a source of light placed here, and it's creating light. And then where the light rays meet, that's the image of that source. And that's the image as dash. And that means that if this distance is dO, distance to the object, and this distance is dI, we can simply write the equation 1 over d0 plus 1 over di equals 1 over f. And I think we need to find the focal point. Yeah, and the radius of the curvature. Absolutely. So the object is 30 centimeters, so 1 over 30 plus 1 over 20 equals 1 over f. So 1 over f is equal to, that's 60, and that's 2 plus 3. So that's 5 over 60. So it's 1 over 12. So focal distance is 12 centimeters. And the radius of the curvature is 2f, which is 24 centimeters. We already know that. We already know that radius is double the curvature. Lovely. All right, so this is how to use the the spherical mirror formula. Ray construction with a lens. A convex lens forms an inverted image twice the height of the object. A convex lens. Convex lens, that means it is a converging lens, right? A convex lens forms an inverted image twice the height of the object. Well, if we have an object, yeah, we know that the principal ray passes through this point, and we can use the squares to construct the image. So the image is double the height. So because one of the principal rays passes through this point, we know that this is the object and this is the image. And now just a simple matter of construction. So we draw a parallel beam, parallel ray, and the parallel ray will always pass through the focal point. So that is the focal point. And so the focal point is somewhere here, F1, and we can work out the draw radar, show the object distance in terms of focal length. Okay, we know that the distance to the image divided by distance to the object, that's magnification. That's equal to 2. Therefore, di is equal to 2 do. And then we just write the thin lens equation. Thin lens equation. And that's 1 over do plus 1 over di equals 1 over f. It's the same as the equation of the mirror. So 1 over d0 plus 1 over 2 d0 equals 1 over f. So we multiply this by 2. So 3 over 2 d0 equals f, 1 over f. And so d0 is equal to 3 over 2f. So 1.5 focal points. Lovely. And that does make sense. If this is f, then this distance is d0, which is 1.5 f. Does look very realistic. We can check if we take a lens. So what do we have? The focal distance. Let's take the focal distance to be 10 for simplicity. And okay, so this is 10, let's say that's in millimeters, right? It is in centimeters, but let's just imagine it's in millimeters. So this is 10 centimeters, and we need to place our object 15 centimeters away. So we place it here. And yeah, let's check. The pencil is 50 58 millimeters, and the image of the pencil is 116. Makes perfect sense. Ta-da. Okay. Two positions of a lens, a screen and an object are placed 1.2 meters apart. So you have a screen, and an object. So you have an object, and there's a lens somewhere here. Lens. The lens is allowed to move. So you can move the lens, and by moving the lens, you can create a sharp image of something. I can demonstrate that. Think. So if I take, this is my screen, and this is my lamp. You don't see my lamp, but it doesn't really matter that you see it or not. But if I take my lens, so I can create a sharp image of my lamp. I think I can. Yeah, here it is. Here's a sharp image. So, and it turns out it's actually a very good image. It's difficult to explain how good it is. What I'll do is, if I take, can I draw some kind of shape? I think I can. So what I'm going to do is I'm going to draw this star, and I'm going to fill it with red star. So now I'm going to switch off the light, and I'm going to attempt to create an image of that star on that piece of paper. Oh, here it is. You could definitely see it. Oh, sorry, not very good, but you can definitely see something. Here's here's the image of a star. You see it? You see the star on the piece of paper. Yeah. Yeah, so have some fun with lenses. If you have a lens at home, this is a very obvious thing to try to do. Right. And the image is on the screen. So the image is going to be upside down because it is a real image. Only real images can be shown on a screen. So therefore, it is on a screen, it is real image. It is real. Right. What do we know? Well, we know that this distance is x. Let's say this distance is x. And this distance, well, it's 1.2. Let's do it in centimeters. 120 minus x. So the distance to the object and the distance to the image is that. Common example is two different positions separated by 20 centimeters. So we have two different positions, x1 and x2. And it turns out that, okay, so position one, d0 is x, and di is 120 minus x. And then we move it by 20 centimeters, position 2. d0 is x plus 20, and di is going to be 120 minus x plus 20, and that's equal to 100 minus x. And in both, the focal distance is the same in both cases. So we just write two equations. 1 over x plus 1 over 120 minus x is equal to 1 over f. And 1 over x plus 20 plus 1 over 100 minus x equals 1 over f. We're not really interested in the focal. Well, we do need the focal distance, but to find the focal distance, we need to find x first. So let's do that just by equating the top and bottom. So 1 over x plus 1 over 120 minus x. I think we're going to be in trouble now. X plus 20 plus 1 over 100 minus x. Because of the crazy maths I'm about to embark upon. Is there an easier way of doing it? I don't think there is. Yeah, it's going to be a quartic equation. So brace yourselves for a quartic equation. So it's going to be x plus 20 multiplied by 120 minus x multiplied by 100 minus x plus x x plus 20 100 minus x. Okay, cubic equation, not that bad, not the end of the world. And equals x 120 minus x 100 minus x plus x. So I'm just multiplying everything by all the denominators. 120 minus x plus 20. Okay. So 120x minus x squared plus 2400 minus 20x multiplied by 100 minus x plus x 100x minus x squared plus 2000 minus 20x equals x 12,000 minus 120x minus 100x plus x squared. I'll be very surprised if I don't mess this up. So plus x 120x plus 2024 2400 minus x squared minus 20x. Is it 12,000? It is 12,000. Okay. Right. 12,000 x. Oh, let's do that. 100 and 100 x. 10,000 x minus 100 x squared plus 240,000 minus 100 x squared minus x cubed minus 2400. Okay. Right. Um, plus x cubed. Oh, yes, it is plus x cubed. Sorry, I don't have the energy to do this right now. Let's just what if do you think I can ask ChatGPT to solve it? And and skip. Ah, let's see if it can solve it. I don't know. I don't know if it can. But yes, I do have an answer, and the answer is 29.2. So the distance. So for the focal point, so the answer. The focal point is 29.2 centimeters. Let's see what ChatGPT said. Still analyzing. Okay, it's doing something. X is 50. Okay, so it's solved. It's there, 50. ChatGPT actually solved it, and it says X is 50. So hopefully F can be solved. And let's see, F 1/50 plus 1/70 equals 1/F. So F is 50 times 70 divided by 120. And that's 50 times 70 divided by 120. 29.2, yay! 29.2, brilliant. It did manage to do it. Okay. It didn't solved by ChatGPT. Solved. And it's 50. Wow, that's impressive. Okay. Moving object and image speed. Right, so let's an object moves towards a convex lens at constant speed v0. So we have a lens. and we have an object. Object is moving towards the convex lens at constant speed v0. At a certain distance, the object is located at a distance 2f from the lens. Determine position of the image of that instance and determine this instantaneous speed. Right, so we have the image is somewhere here. Image of the object. And let's see just to touch base. What are we dealing with? So let's make the lens somewhere here. And so this is what 18 centimeters. So as we're passing through this point, okay, so the penguin is moving from left to right, and you can see the image is moving away from the lens. Okay, from left to right, and it's moving away. Okay. So it's passing through this point. So this is the point that we are looking for. Right. So this is the focal point. This is double the focal point, and the object is passing through that point. So this is DO, and we write 1 over DO plus 1 over DI is equal to 1 over F. And first we need to find DI. Well, we know that DO is 2F, so 1 over 2F plus 1 over DI equals 1 over F. So 1 over DI is equal to 1 over F minus 1 over 2F. So we multiply, this is 2 minus 1 over 2F, which is 1 over 2F. And that means that DI is 2F. Oh, so the image is exactly the same distance away, so 2F. Now, B. We are going to find the velocity of the image. To do this, we're gonna write this equation, d0 plus 1 over di equals 1 over f. And I'm going to express d0. No, I'm going to express di in terms of d0. And to do this, di 1 over di is equal to 1 over f minus 1 over d0. And that's d0 minus f over f d0. So di is f d0 divided by d0 minus f. That's the distance to the image. And now, velocity of object v0 is actually the rate. Well, it's moving from left to right, so d0 is decreasing. It's the negative rate of change of d0. Negative d0 dash. Why negative? Because the distance is decreasing. So if the velocity is positive, the velocity would be the distance would be increasing. But the velocity is negative. Sorry, the velocity is positive, but the distance is decreasing. So it has to be negative. That's why I put a minus in front. Velocity of the image. We know that the image is moving further away from the lens. So vi, that's the derivative of I with no minus. Okay, so what I need to do is I differentiate the expression. Differentiate And I think I need to use the quotient rule. Using the quotient rule. So di dash, so vi is di dash, and that's equal to f multiplied by d0 dash multiplied by d0 minus f minus f d0 multiplied by d0 dash divided by d0 minus f squared. And we know that d0 dash is minus v0. So vi, the speed of the image, is going to be the focal point multiplied by d0 dash, which is minus v0. d0 is 2f minus f minus f multiplied by 2f multiplied by minus v0 divided by 2f minus f squared. All right. So, and this is going to be f squared, so minus v0 f squared plus 2 v0 f squared divided by f squared. So f squared cancels, and we're left with 2v0 minus v0, which is just v0. Oh, so the speed of the image at that particular point is exactly equal to v0. But in general, vi is going to be minus v0 f d0 minus f minus plus v0 f d0 divided by d0 minus f squared v f d0. So that's going to be v0 f squared divided by d0 minus f squared. I think that's it. Yeah, brilliant. Okay, I'll leave you here. So hopefully that was useful. We did lots of maths today, in fact, with the equation. So I hope you got a sense of this equation. I also hope you got a sense of what mirrors do, because it's not very obvious. These things are not that straightforward. I'll leave you here. I'll see you in 2 weeks' time for some maths. See you all. Oh, I don't think it's 2 weeks' time. I think it's later, but let's double check. Why not double check? Oh, so oh yes, 2 weeks' time. Set theory. Lovely. See you on the 10th of March. Welcome. Thanks, ChatGPT.